Perfect. Okay.
Good.
All right. Good deal. All right. Well, thank you everyone for taking the time today. We're going to talk just a little bit about laboratory and fume exhaust systems. As Tracy said, my name is Justin Zahn. I'm an application engineer here at Greenheck. My main job is to work with our laboratory and fume exhaust line. I also do a little bit with our garage transfer fans as well. So that's our ductless garage fans. And then I also work a little bit on the data center side. So I work a little bit with Meta and Amazon in particular. Some of the basic guidelines that we'll go over today, so we'll go over the lab existing system guidelines as a whole, what to be aware of in the industry, basics of operation, and then some of the lab exhaust products. And then to wrap up, we'll actually hop into, time permitting, we'll hop into a virtual lab, a little bit more interactive, and it's a nice little change up from the PowerPoint. So, what are the main objectives of a laboratory exhaust system? The main objective is to remove hazardous effluents or contaminants up from a workspace or lab, whatever it may be, expel them into the atmosphere and get them pretty much as far and away from the general population or any makeup air systems on the roof. So the biggest thing is to prevent re-entrainment. We want to make sure that our plume height's getting high enough up there where we don't have to worry about any possibility of that coming down too soon and coming in contact with someone on the ground. So we design our laboratory exhaust fans around two key standards in the industry. The first standard is going to be ANSI Z9.5, which states the discharge velocity coming out of the top of these fans needs to be 3,000 feet per minute or more. Typically, it is more. We stand by this standard. That standard, though, has actually now changed in the industry. Now it is up to you or whoever's designing that lab space to determine what velocity you truly need. Like I said, Greenheck, most manufacturers, we're still going to recommend 3,000 feet per minute or more. Reason being, we know it's safe, we know it works. It's the standard that's been followed for quite some time now. One of the reasons why the standard has changed in the industry is, these fans are energy hogs. That's kind of the nature of them. So if you don't have to have your fan running at 3,000 feet per minute, why would you, right? And any way you can save energy, most people are on board with that and want to do it. But again, 3,000 feet per minute is what we still want to recommend and still want to stick with. So that's standard number one. Standard number two is going to be NFPA 45, which states that these fans need to be 10 feet tall minimum. We get the question all the time, can you make these fans 8.5 feet tall, 9 feet tall, whatever it may be? The answer is always no. We will never build a laboratory exhaust fan under 10 feet tall. That is, a hard rule that we follow. We do understand that, especially working with architects, that they want these fans shorter to protect, I guess, the looks of their building. A lot of architects don't find these fans too good looking. We find them beautiful. They do not. So it's a constant battle going on between us and them. But just to keep in mind, again, 10 feet tall is the absolute bare minimum that we will go to. And most of the time, these systems are much taller than 10 feet tall. So just to reiterate, the two standards, ANSI Z9.5, 3,000 feet per minute discharge velocity, and then NFPA 45, these fans have a minimum height of 10 feet tall. So when we talked about ANSI Z9.5 at 3,000 feet per minute and how that has now changed in the industry, well, people that are aware that that standard has changed, we tend to sometimes get a little bit of pushback when people say, why are you recommending 3,000 feet per minute? Well, we know that with 3,000 feet per minute, we can usually 3,000 feet per minute or more, we can usually achieve our targeted plume height. And again, we know it's safe. But for those that want to push back on that 3,000 feet per minute rule, we say, you're more than welcome to go get a wind-wake analysis. Basically what that is, for those of you who do not know, is, let's say these fans are going downtown Atlanta. Obviously, there's a lot of buildings around. a lot of tall buildings, I should say, that in return would affect the turbulence coming off those buildings, the wind coming off those buildings. So, which would have a direct effect on your plume height. So what they do in this wind wake analysis, they will create a 3D printed model of these fans, whether that's a centrifugal model or a typical mixed flow laboratory exhaust fan. They will place that 3D model in another 3D model of, let's say, downtown Atlanta. They will then place both these models in a wind tunnel of some sorts. They will then blow smoke up that fan, some kind of colorful smoke, rotate that table or the 3D model, and then study as they're blowing wind across it, study how that plume is affected by certain wind speeds. It's a very, very interesting tool that we see every now and then in the industry. But usually what happens when someone wants to push back on the 3,000 feet per minute rule, we tell them to do this. They go get a quote. They come back and they say, okay, we'll stick with what you guys are saying at the 3,000 feet per minute. Reason being, obviously it's extremely expensive, very, very pricey, which is why most of the time, when people see that, they'll come back and the 3,000 feet per minute doesn't sound so bad anymore. But nonetheless, it is a great tool at everyone's disposal. We do see it, every now and then being utilized on much larger jobs. But again, most of the time that 3,000 feet per minute or more is what people want to stick to. So moving on, just a couple of, we can call it almost housekeeping items, because I'm sure everyone knows what AMCA is, and everyone's familiar with it. But what a lot of people don't know is there are two ways to say you're AMCA certified. One way is incorrect, one way is correct. The incorrect way is saying laboratory exhaust fan systems shall be tested in accordance with AMCA standard 210 or 260. The key thing in this sentence is you never see anything about the certified rating seal. So you don't see anything about how you're certified to actually bear that seal on your products. Why that's so important? AMCA is that third-party testing service. So basically, it's a way to solidify that all the data that the manufacturer is putting out there is 100% accurate. Obviously, especially when it comes to this market, these are life safety applications. So you want to be as accurate as humanly possible. Being AMCA certified is the way to do that. The correct way to say you're AMCA certified is laboratory exhaust fan systems shall be tested in accordance with AMCA standard 210 or 260 and are licensed to bear the AMCA certified ratings seal. Why am I telling you this? Just because there are still a couple of manufacturers out there that will have certain products that maybe aren't AMCA certified, and we want to just let people know or have people be aware of that, just because, again, you want to make sure that all the data, especially in this kind of market or industry, when it comes to laboratory exhaust systems, you want to make sure that all the data that we are providing you is 100% accurate. You want to make sure that these fans are going to perform exactly the way we told you they were going to perform without any surprises in the field. So again, we want to make everyone aware that there's two different ways to say you are AMCA certified. One is being correct, one is incorrect. So moving on now, we will talk just a little bit about the best practices and the worst practices as far as design guides when it comes to these laboratory exhaust systems. So we'll start on top here where it says best. It's really not all that complicated when it comes to these systems as far as how you want to design your stack. The best thing to do, straight stacks with no caps or heads. So nothing to potentially deter that plume height. You want to make sure that plume height can flow freely out of that fan without any obstacles getting in the way of that. What I want to do is go to the bottom of the screen now where it says pour should not be used. We want to avoid caps on these. Sometimes people laugh and say, why do you even talk about this? But it's still a question that comes up every now and then. The biggest thing that we want to avoid is going to be this gooseneck looking stack on the side here on the far right. Just don't use that. We see some pretty weird designs out there. Sometimes people think, what was the designer thinking? This gooseneck completely defeats the purpose of having a laboratory exhaust fan. The only thing you're doing is dumping whatever you are exhausting back onto that roof, which then obviously has the potential of coming in contact with whoever's on that roof or other makeup air systems that are on that roof. I like to tell the story, that when I first started at Greenheck, me and my boss were traveling to a specific rep's customer. We went up on a roof. This fan was completely gated off. We got a little bit closer to it. We noticed that it was a gooseneck stack. Needless to say, we got out of there pretty fast because whatever was being exhausted was just being completely dumped right back onto the roof. And again, just completely defeats the purpose of having a high plume type of fan. So really quick, what I'm going to touch on is just the two different ways to calculate your plume height. The first way, the simplified way to calculate plume height is through a modified Briggs equation. This is the equation that was previously used in the industry, not so much anymore, just because it's not nearly as accurate as your momentum flux equation. Why? There's still two equations out there. Well, at the end of the day, it's a sales tactic using one equation to the other. Momentum flux, definitely far and away your most accurate way to calculate your plume height. Modified Briggs, we're not saying it's not accurate, but it's just not as accurate as momentum flux. People still use modified Briggs for one main reason. I should say some competitors will use modified Briggs for one main reason, and that is just because you typically get a higher plume height with it, which at the end of the day, it's just not as accurate as a momentum flux. And these being life safety applications, you want to be as accurate as humanly possible. We default to momentum flux in our selection program, just because, again, we know it's far more accurate than modified Briggs, but we do keep modified Briggs in our selection program for when those questions come up about, how come competitor X or competitor Y has a higher plume height than you, as in Greenheck. We simply switch our selection from momentum flux to modified Briggs, and we're usually right on the money. And at the end of the day, there's not really too much rocket science that goes into this. If you have the same fan, same wheel, same motor, same everything, I don't care really who you're going against. The plume height should be relatively close to the same. One should be 5 to 10 feet higher than the other. And again, we just want to make people aware of that and always question how your plume height is being calculated. You always want to push for momentum flux, but just be aware that modified Briggs is still used. So moving on, talking about plume height a little bit more. There are a couple different programs out there or selection programs out there that have different tools that can be used within them. One of them that we like to use on here is a nice visualization on how high your plume is going to be at a certain point downstream. So basically how it works, you select your fan, you input your chemical concentration if you know it. Sometimes, obviously, that's hard to come by, or that information is hard to come by. You can adjust your wind speed. So depending on where these fans are going to be, you can adjust it anywhere between 10 to 30 miles an hour, or whatever it may be. And then basically how it works, you're going to see your laboratory exhaust fan on the roof here. And then you're going to see your effective plume rise. What you can do then is pick some point downstream here. So if you look over to the right, there is this little dot on the screen. That little dot could be a building or something else that we want to make sure that this plume is well diluted by the time it hits that point downstream. So basically, when looking at this graph or this image, you will be able to tell how diluted your plume is going to be by the time it hits a certain point, just by looking at this little table down here. Obviously, it's an estimate, so it's not hard data, but we found this to be extremely accurate. when it comes to calculating plume height. And it's kind of a almost like a safety net at the end of the day, where you feel a little bit more comfortable about the data we are giving you. And again, if you have customers or whoever you are working with that is concerned about a building somewhere downstream, well, you are able to utilize this tool, or your reps able to utilize this tool to be able to give you a more accurate answer on how diluted that truly will be downstream. So really quick, we'll talk about older lab designs, and then we'll kind of go into the newer lab designs. So the older lab designs, you usually would have one hood and one fan. Pretty straightforward. One thing about this, obviously, with that many hoods, that's a lot of fans to maintain on the roof. So that's why, sometimes, or most of the time now, the industry is moving more towards the manifold exhaust system, where you'll have multiple hoods going up into some kind of common ductwork and then into the fan. A lot more efficient, where you only maybe need 1 or 2 fans on the roof compared to 10 to 15 fans on the roof. One thing to keep in mind with this system is there are certain chemicals that you do not want to mix, as I'm sure everyone is aware of. So there still may be times where you maybe need to have 1 fan per hood, just depending on what's going on in the space below. But most of the time, standard jobs, you will have multiple fume hoods going up into some kind of common ductwork and then into the fan. One thing about the older system that was kind of nice is, if you had a system problem with one of your fans, where if your fan was not performing the way it should be performing, you know exactly where to look, from the hood all the way up to that fan. There's really no guessing going on there, compared to as now, where if you have a system issue, there's quite a few places you need to look on there in order to determine what's truly going on within that system. So there's pros and cons of both, but typically the manifold exhaust system is what you will see mainly in the industry. Okay, so now we are going to talk just a little bit about pre-engineered versus built-up systems. Especially in this kind of market or in this industry, there are, a lot of people want to save money, and because at the end of the day, these systems are expensive. We understand that. That's just kind of the nature of these systems. But what we want to stress is sticking with pre-engineered systems. Why? Because built-up systems, there is a lower purchase price of the fan, but there's a much higher install cost. And then the performance on these fans, a lot of it is not certified. Just because, you may be taking different pieces of, one manufacturer to the other, and you truly don't know how well these fans are going to perform out in the field. So there could be some surprises out there, and then obviously a lot of headaches to follow. Another thing with this built-up systems is you're going to notice this system is really not that tall, but you're going to notice guy wires are required on this. Why these systems need guy wires for the built-up systems is because most of the time this roof curb is provided by a third party, and you don't know how, whatever fan you're ordering from, you don't know how that, or fan manufacturer you're ordering from, you don't know how that's going to sit on that curb, meaning you don't know how stable that's going to be on that curb, just because it was never previously tested. So something to keep in mind, most fans, all of our fans come with 125-mile-an-hour wind load rating without guide wires. That's if you use our curb. If you go to a third-party curb, a lot of times that wind load rating would be voided and guide wires would be recommended at that point. Sticking with pre-engineered systems, so it is a little bit higher purchase price up front, but a much lower install cost. And then the biggest thing with these fans being pre-engineered systems is the performance of these fans. All these fans were tested previously, so all potential performance losses are already accounted for, compared to the built-up systems where none of that is accounted for. So that's, when I said you might have some surprises out in the field with the built-up systems, usually that is what happens. With pre-engineered systems, in the long run, it just saves everyone a lot of headaches. And again, it's just, these fans are going to perform the way we told you they were going to perform once they hit the field. Okay, so Now talking about the lab space itself. So in labs where, or most labs, I should say, there are three control loops that stay constant. The first control loop is going to be your hood velocity. So your hood velocity, your face velocity, I should say, typically that's going to be around 80 to 100 feet per minute with that air moving across that hood. We usually don't see anything more than that, just because if that air is moving faster than that, you run into the possibility of, ruining whatever you are working on within that workspace. So typically 80 to 100 feet per minute, that's control of number one. Control of number two is going to be how you pressurize your rooms. So typically, it's going to be a negatively pressurized room. You will run into different situations where rooms may be positively pressurized, mainly OR suites, maybe some different isolation rooms. But usually it's going to be a negatively pressurized room. So that's control of number two. Control of number three is going to be your duct static. And how we control that is through our bypass air plenum. So as the demand from the lab space decreases, so let's say these, hoods shut down, the doors are shutting down. As they shut down, obviously we need to get that duct static back to where it needs to be. And with that as well, we need to pull in some extra air from the outside in order to maintain our plume height. How we do that is all through the bypass. So we will modulate that open in order to get that duct stack back to where it needs to be. And on top of that as well, we will be able to maintain our targeted plume height on there. So three control loops. I don't want to spend too much time on this, but the face velocity, 80 to 100 feet per minute, typically how you pressurize your room, typically a negatively pressurized room, and then your duct static, which is controlled by the bypass air plenum. So moving on now, we'll actually get into some of the products themselves. We'll start with the smaller inline product. So the Vector H, this is one of the products that you will see used for smaller jobs out in the industry. We have single fans capable of doing right around 24,000 CFM up to about 4 inches of pressure. These fans, again, come with 125 mile an hour wind load rating, belt or direct drive construction. One thing with the direct drive option that you'll notice on this screen here, this is fairly new to the industry. I would say probably within the last 2 to 3 years, this has really hit the market. The direct drive option we call a plug and play type of fan. So very easy to set up, very easy to maintain. We know that, maintenance is becoming more of a hassle for these fans, and finding people that actually want to work on them can be a job in itself. So what we have done with our design is the picture that you see right here, where that motor is kind of floating. You are actually able to pull that motor out in the field just by this panel that motor is attached to. So when you unbolt this panel on the outside of the fan, you can pull out the motor and the wheel all together. So just making it a little bit easier to work on, making the maintenance a little bit quicker to be completed. And with that, so sometimes people think that these motors sit within the airstream. And in this particular case, they're not 100% wrong, but still, these motors will never come in contact with that airstream because they actually sit within an isolated housing within that fan. Reason behind that, we don't want anyone coming in contact with whatever is being exhausted. Or any parts of that motor coming in contact with whatever is being exhausted out there. Again, just a neat little design point. We are one of the few in the industry that can actually offer this type of design. There are a few other ones out there that can offer smaller inline direct drive fans, but the design is not like ours. We want to have our equipment be easy to work on. We have a saying here at Greenheck that we want to be easy to do business with, but we have a non-written saying that we want our equipment to be easy to work on. Well, this Vector H truly does help with that saying on there. So that's our smaller inline fan. You'll see these on high school science labs, college science labs, any job of non-significance, essentially. So lower CFM, lower pressure, that's where you'll see these types of fans. One thing that is not talked about that much in the industry is restaurant exhaust. So you will see these fans from time to time on restaurant exhaust. We can get them with the grease exhaust rating. A lot of times, people ask, why would you want to put a laboratory exhaust fan on a restaurant? What we always tell people is if you live next to, your favorite burger joint, steakhouse, whatever it may be, that may smell good for a while, but you're not going to want to smell it every single day of your life. So that's where these fans come in. The main difference, having these with a grease exhaust rating is, you'll have a vented roof curbs to prevent heat buildup, and then there'll be a clean out located in the lower plenum box, to clean that grease out. So still 10 feet tall. We won't not going to be wavering on that, but obviously no bypass would probably be the biggest difference on here. So moving on, we are now going to talk about the mixed flow option with a dilution nozzle. So these are the types of fans that people probably associate laboratory exhaust fans most with in the industry. These fans are capable of doing right around 80,000 CFM up to about 8 inches of pressure. So definitely built for larger jobs. Still have that 125 mile an hour wind load rating without guy wires. Spark C or Spark B is an option for you. Belt or direct drive arrangements as well. When looking at the design features of our mixed flow fan, and what kind of sets us apart just a little bit in the industry, the first one is going to be the bifurcated fan housing. That is more common in the industry, but a lot of people think that this motor sits within the airstream. That is not true. That motor actually sits completely isolated out of the airstream, sits in a bifurcated housing where that air can actually move up and around that motor. So again, if you do need to work on this fan, for whatever reason, you don't have to worry about coming in contact with whatever is being exhausted. Obviously, where that motor sits is a little bit harder to maintain, but because it is a direct drive option, there's less maintenance to begin with. Another key design feature with these fans is going to be the isolation damper. So this isolation damper actually sits above the plenum, as you can see, and actually sits on a track. So why it sits on a track, we are able to easily remove and install the damper, no problem, at an extremely quick rate. Why it sits above the plenum? Again, if you need to get at that damper for whatever reason, we don't want you to have to put on a hazmat suit and actually crawl within the plenum to maintain that damper. Now you are just simply able to remove it, slide it out on a track. And again, it's a really, really neat service feature of these fans that a lot of people really like. One thing with this isolation damper on here is you're going to we get a lot of questions about people wanting to use different types of isolation dampers within this fan. We usually try to stick with the pre-engineered system when it comes to the isolation damper, just because a lot of times, if you don't have these isolation dampers sized 100% perfectly, you could potentially run into the risk of, if you're running some type of redundant system, whatever fan's off, you could run the risk of potentially pulling air back down through that fan, and then spinning that fan backwards. But at the end of the day, everyone knows that'll probably be a pretty big headache, and you're gonna have to perform some maintenance on there. So that is a really, really important piece of that fan. When people ask, can we use certain isolation dampers within your fans, we usually say no. These are perfectly sized 100% through our selection programs. There's really no guessing that needs to be done on these. And again, we want to stress the importance of sticking with the properly sized isolation damper. Moving on, another key feature when it comes to these fans is going to be our plenums. So our plenums actually come with 4 removable side panels. Why they come with 4 removable side panels is, we understand that when the job first comes in, so that first inquiry that comes into us here at Greenheck to when these fans are actually installed later in the field, there's a lot of things that can change in between that time. One of the things that changes the most is going to be your plenum or your side inlet. Or bottom inlet, wherever that's going to be. We want to make it easy for you or whoever's installing these fans out in the field to be able to essentially choose your inlet while you're out there. Obviously, you can still let us know where your inlet's going to be, but if something changes last minute on a job, like where the inlet is going to be placed, you are able to remove these side panels on here and simply connect your ductwork and you are good to go. That cannot be said for a lot of competitors out there in the industry. Once you choose your inlet, you better make sure that that's exactly where that inlet's going to go. Otherwise, you could potentially be, dead in the water out there. We want to, we want to adapt to whatever, the job throws at us. And having these 4 removable side panels on our plenum is one way to do that. So here's a better image of the direct drive bifurcated housing where that motor sits. Again, that air move up and around that motor and then into the nozzle, and then out into the atmosphere. So a couple things about, belt or direct drive. Direct drive, obviously used a lot in the industry, but we do still see belt drive a decent amount as well. When you have jobs, certain jobs may be requiring belt drive and certain jobs may be requiring direct drive. Well, then there's some jobs that could go one way or the other. With belt drive, sometimes people like it a little bit better because it is a little bit easier to service. That motor sits on the outside of that fan in that box there. Very, very easy to get at, easier to maintain. But with belt drive, obviously comes a little bit more maintenance. So that's when sometimes people want to go to the direct drive. A little bit harder to maintain, but a lot less maintenance on it. So, it's kind of a trade-off. When you have those jobs that could go one way or the other, we have reps that have customers that only want belt drive, and then we have reps that have customers that only want direct drive. So it's sometimes comes down to preference on what you would like. So here's a couple of configurations that you will typically see in the industry, anything from 1x1 to 6x1 to 2x3 to 2x2. These are, you can have some very, very large systems with a relatively small footprint. Obviously, these systems can get really, really big depending on how many fans you have. But why a lot of people like the mixed flow fan is because, it is somewhat compact, where the fan is more tall instead of wider. So moving on now, we'll talk just a little bit about the high plume offering on the mixed flow fan. So these fans with this type of nozzle capable of doing right around 60,000 CFM up to still about 8 inches of pressure. Again, still you can get them in belt and direct drive. The only thing you're really changing on here is the nozzle. And we'll talk just a little bit here in a little bit about, the different types of nozzles and when to use them. So here are some of the pros and cons of using an inline fan. Pros, like we talked about, much smaller footprint on here, low to medium pressure capabilities, and then pre-engineered systems, again, like we talked about. The biggest con that we see, especially with bigger systems, is going to be the taller finished heights. So you'll notice this man standing right here next to one of our vector systems. Even though these are belt drive fans, you're still going to need a little bit of help getting up to where that motor is in order to maintain it. So again, not as easy to access, which I would say is the biggest downfall to these fans. But again, if roof space is limited, these mixed flow fans are a great option for you. So moving on now, a fan that we like to push most in the industry, I should say, is the Centrifugal high plume dilution blower. These fans are built for bigger jobs, so capable of around 140,000 CFM up to about 14 inches of pressure. Again, these fans they're built for bigger jobs. So jobs, of more significance. Sometimes people ask, why do you have a fan or laboratory exhaust fan capable of doing 140,000 CFM up to about 14 inches? What we like to tell people is we just want to be able to adapt to whatever's thrown at us. And this fan allows us to do that. One thing with this fan is so you have a couple pros. They're a little bit more efficient, the higher pressure capabilities, and the biggest thing that a lot of people like about these fans is where that motor is located. So right at ground level, very, very easy to get at, very easy to maintain, which a lot of people like. The cons is going to be the larger footprint on these. So, if you have multiple fan systems, let's say you have a 4 or 5 fan system, sometimes it's just simply not in the cards. There's just not enough room on that roof roof deck in order to install one of these fans, just because of all the other systems that are on the roof. But again, if you are able to go this direction with our centrifugal fans, we definitely recommend it, just because, again, efficient, and then where that motor is located as well. So a lot easier maintenance. Talking about the footprint a little bit, if you look at 1x1 to 4x1, again, these systems can get extremely large, which sometimes, you can't do it out in the field, just because the roof space won't allow it. One thing that we want to touch on here a little bit is going to be the nozzle comparison. So we talked briefly, about having the dilution nozzle and the high plume nozzle. A lot of people think in this industry that when it comes to laboratory exhaust systems, that you have to have the dilution nozzle. That is simply not the case. We want to change that narrative in the industry. Again, there's no code saying you must have dilution. We want to change that narrative as far as you are able to put a high plume nozzle on these fans, and that is the more efficient option. So if you look at your dilution nozzle compared to your high plume, we selected a fan at 30,000 CFM at about 5 inches of pressure. Look, first we want to point out is the brake horsepower on this. So if you look at your dilution nozzle, you're at 55.1 compared to your high plume 43.0. So a pretty significant difference that you will notice on there. Why the dilution nozzle has more or requires more brake horsepower is, you're entraining more air. So you're pushing more air through that fan, which obviously in return requires a little bit more power. One thing with the dilution nozzle, sometimes people think that you get a higher plume height with the dilution nozzle. That is not always the case. In this particular situation, at this fan that we selected, our plume height was right around 50.4 compared to the high plume 54.0. The whole point of showing you this is not to discredit the dilution nozzle at all. It's still definitely needed in the industry. If you have jobs that have an exhaust with an extremely pungent odor, or if you have jobs that have an exhaust that is extremely hazardous, and if you're in a large city and they need to be diluted, or that exhaust needs to be diluted a little bit more before it hits that airstream, these nozzles are definitely a great tool. What we just want to tell people is, do your homework. Do you truly need the dilution nozzle, or could you get away with a little bit more efficient option? Because most of the time, when they select these fans or are looking at these fans, they think they have to have dilution, and that's simply not the case. So where you'll see some of these fans applied, university labs, pharmaceutical companies, biotech companies, any job of more significance compared to the smaller inline fan that what we talked about before. Great for bigger jobs. We have a lot of capabilities with these fans, but you wouldn't see these fans on a high school lab or any job probably under 10,000 CFM or anything like that. But built for bigger jobs, and multiple configurations that we are able to offer, based off your needs. So really quick, we'll talk about 11:43. So I got to kind of get moving here, but we'll talk really quick about sequencing the fans back online and offline, and when to do it, how to do it. One thing I want to touch on before we get moving with the sequencing these fans, or how we sequence these fans back online and offline, is the worst thing you can possibly do for your fan is let it sit idle, meaning where it's not running at all. We want to make sure that we are rotating our fans. If you have a multiple fan system, never leave a fan just sit. That is the worst thing for it. We get more calls on that every month about fans sitting for long periods of time, and then all of a sudden they want to turn them on, and for some reason they're confused as to why it doesn't work. Well, again, we just like to tell people, as you're moving these fans or sequencing these fans on and offline, just make sure you're rotating them as far as how many hours they're operating, and just make sure that, again, no fan is sitting idle. So we'll start just your simple 10,000 CFM application here. So both fans taking on 5,000 CFM. you have a CFM coming from the lab space around 7,500 CFM, and then you have your bypass air dampers pulling in around 2,500 CFM. As the demand from the lab space decreases, so now we're at 5,000 CFM, you're going to need to pull in more bypass air. Well, as it decreases even more, so now we're only at 4,500 CFM, you're able to shut one fan off. How you want to shut it off is, fan and isolation dampers should be powered off at the same time. Or what we like to recommend is isolation damper be shut off first, then shut the fan off after that. Why that's so important? We talked earlier before about the fan potentially spinning backwards, and shutting that isolation damper off first can prevent that from happening on there. So same thing with sequencing them back online. If your CFM from your lab space is now increasing again, as that increases, you could pull in 5,000 CFM from your lab space and then 5,000 CFM from your bypass air dampers. And then how that works, by sequencing them back online again, pretty much the same way as sequencing them back offline is stage fans, isolation dampers should be powered open at the same time as fan start, or turn on fan first, then open the isolation damper. So again, just a safer way to turn on these fans. So moving on now, for a couple of different accessories that you will see out here in the field. We'll start with your standard bypass plenum, single wall construction, separate access points, 4 dampers. Again, we talked about the removable side panels on here. The variation to this is going to be your double wall bypass plenums. This is used to insulate the exhaust airstream to prevent condensation. That's mainly the only use for it. One thing with these bypass or double wall bypass air plenums is, you're adding a decent amount of weight to your roof deck. So that needs to be kept in mind. And then with that as well, lead times typically tend to go up as well. So it's just something to keep in mind. If jobs do require it, we are able to offer it, but most of the time, the standard bypass plenum is typically all you're going to need. Moving on, these fans, obviously sound is becoming more and more of an issue in the industry. So we have come up with different solutions in order to combat some of that sound. One thing is, the attenuated wind band and wrap, as you see on the screen here, used to reduce sound. Another thing is the inline discharge attenuator. Another way to reduce sound. One thing to keep in mind when adding these two types of attenuation, typically the inline discharge attenuator, sometimes depending on how tall your system already is, when adding these types of attenuation, you could potentially run into the need to use guy wires. So a lot of people, they don't want to deal with guy wires. That's kind of the way the industry is moving. So that's just something to keep in mind. So what I like to recommend to people is start at the bypass attenuator. Why we like to start at the bypass attenuator is depending on how much CFM you are pulling through your bypass damper, that typically tends to be one of the louder parts of the fan. So having being able to combat some of that, one of the louder parts of the fan while eliminating the needs for guy wires is a great way to go. Yes, they are heavier. They do add a decent amount of weight to it. But again, you're completely eliminating the need for guy wires because your system's not going up at all. Another option that you will see a lot in the industry is a jib crane option. So provides means to remove motors or other parts of the fan. Great tool. The whole point of it is to, take the responsibility out of someone else's hands and then put it back into your hands where you're not waiting on a crane or whatever it may be. Obviously time is of the essence a lot of times with these systems. So the more you can do yourself, the better. Well, the jib crane is a great way to not have to wait on somebody. So real quick, energy recovery systems for lab exhaust. As I said before, laboratories are energy hogs, and laboratories are 100% ventilated. 50% of the energy used in a laboratory is attributed to ventilation. And then the biggest thing, what we like to make sure people know is energy recovery and properly applied makes sense for labs. It does not always make sense. If you have lower CFMs, there's really no point in adding energy recovery. Typically, we see, well, out west in I should say California, we're starting to see jobs at 10,000 CFM, 8,000 CFM that they're requiring energy recovery on there, which is, as I'm sure you guys know, it's just sometimes or usually just does not make sense. Energy recovery efficiency to around 50%. The biggest thing on here, supply and exhaust ducts are not brought together. Why they're not brought together is we want to, eliminate the possibility of cross-contamination. So we use runaround coils. We want to avoid the wheels and plates on there because then you do have the possibility of cross-contamination, which could obviously be a little bit of an issue out there in the field. So runaround coils, we do manufacture our own coils for our energy recovery systems. Typically, so we have cabinet capacities from 80,000 CFM, or I should say around 82,000 CFM up to, or I should say down to right around 60,000 CFM. We kind of all over the board on there. Obviously we can go smaller than that as well, but typically, we want to push the idea of higher CFM when using energy recovery, just so it makes sense for you guys. And you're getting the best bang for your buck. So here's just a simple image of what our energy recovery system typically looks like. You have your coils on there, no wheels or anything like that, as we talked about. So there's no possibility of cross contamination. So real quick, what I want to touch on, there's when people think laboratory exhaust fans, they think labs. That's, obviously that's their main purpose, but these fans can be used for other different applications in the industry. A couple we'll touch on. One is going to be the diesel generator exhaust. That's a big one. So, if you have these standby generators out, in bigger stadiums or whatever it may be, that exhaust needs to go somewhere. So, and then it needs to be expelled out into the atmosphere somewhere. So that's where these fans do come in. And we see that used quite a bit, especially in stadiums. We do have the ability to pull in higher temps with these types of fans. So one thing with the higher temps is you're going to need to pull in a decent amount of bypass air in order to cool those temps down a little bit. But nonetheless, we are able to accommodate to that. Another place that we see these fans used a lot is going to be the wastewater treatment plants. So, you'll see that's where the dilution nozzle really comes into play. We see that utilized a lot on here. So it reduces the smell of some of these plants depending on where these fans are located. And again, how hazard some of these wastewater treatment plants are. We have the opportunity to dilute some of that exhaust before it hits that airstream, so it's not hazardous to the general population below or any buildings nearby. One last thing that we'll talk about real quick is going to be the emergency ammonia exhaust systems that we see being used in the laboratory exhaust world or for the laboratory exhaust product. Mainly ice arenas. So we see that a lot in ice arenas or any type of refrigeration. We are able to offer ammonia exhaust systems. A little bit different. I mean, they need to be discharged to be outside of 20 feet from property lines or openings in the building, and then they are Spark B construction. They have to be Spark B. It's not that common that we see this inquiry come in, but nonetheless, why I'm sharing all of this with you is just to provide means of some additional knowledge, just so that that it's not just the laboratory exhaust world that we're in that we need to use these fans on. There's other applications as well that we can use these fans on. All right, so now I'm going to jump to our virtual lab really quick. How am I doing on time, Tracy? Am I okay yet?
Yeah, you're good.
Okay.
If anybody needs to jump off, that's all right. We have a bunch of questions that we're going to run through too. So, yeah.
Okay. All right. Can you guys see my screen?
Yep. Looks good.
All right. Perfect. So on the screen, here's your typical lab setup. a lot of this may be a little bit redundant from what we talked about before, but earlier we talked about the three, control loops on here. So you're going to notice that light on there. Let me just change fans here. That light on there is green, where so your duct static sensor. And as the demand from the lab space decreases, like we talked about before, that light turns red. As that turns red, you need to modulate that bypass damper open in order to get that back to where it needs to be. So that was one of the control loops. You have your phase velocity, your reentrainment air coming back in, and then your typical lab setup where you have your hoods, your snorkel, maybe some type of storage cabinet, all going up into some kind of common ductwork, and then up into the fan on here. One nozzle that we really did not discuss was the variable geometry nozzle. So earlier we talked about ANSI Z9.5 and 3,000 feet per minute and how that's changed in the industry. Well, one reason why that's changed is because people want to save energy when using these fans, and if you don't need your fan running at 3,000 feet per minute, why would you? Well, we have come up with a solution in order to maintain high outlet velocities while still being able to maintain, or I should say, save energy. Basically, how it works: as the demand from the lab space decreases, that nozzle up top will narrow up. As that narrows up, your fan speed will slow down. And as that slows down, you will still be able to maintain that 3,000 feet per minute. So again, it's a good design. If people are, if energy consumption is at the top of someone's list, this is a great option to offer them. It's a pretty simple design, just basically two damper blades up top that open up and close as the demand from the lab space, changes. Okay, so one thing that we did not talk about in the PowerPoint was the two types of redundancies that you will see in the industry. The first type is going to be N+1, definitely the most common type of redundancy. You have one fan on, one fan off. As one fan fails, the other one will automatically ramp up, take over this fan's load. One thing with N+1 redundancy, what sometimes is a little bit of an issue for people is, depending on how big your system is, there can be, a decent amount of lag time before that second fan starts up. So, if you're on a really, really critical application, sometimes you can't afford that lag time just because this fan is 100% shut off. So it's not like it's already running 50%. Whereas N-1, you have both fans running at 50%, both taking on half the load or half the CFM. As one fan fails, the other one will automatically ramp all the way up. As that ramps up, this one is obviously shut off. One thing with N-1 is it does require a bigger motor up front. Why does it require a bigger motor up front? Well, when these fans are only running at 50%, so 50% CFM are going through these fans, the nozzle diameter needs to be much smaller up top in order to maintain your targeted velocity. So if one fan then fails, you now have a fan pushing 100% of that CFM up through a much smaller diameter nozzle, which in return requires more brake horsepower. But having these fans at 50%, we call it a hot standby type of option. So depending on where these fans are going, having that hot standby option where the fans are ready at 50%, it ramps up much quicker to 100% compared to N+1, where you have that one fan that's completely shut off on there. So that is mainly what I wanted to get through. I do apologize. Going so fast through here. Obviously, there's a lot of information to cover. And Tracy, I can take your questions now.